we are going to look at what a vector is. A vector, okay. Is this a vector or is this a vector, or some of you would have been using a notation with the arrow on top. Is this a vector or is this a vector, is this a vector or is this a vector? Which of these is a vector? I have given 5 choices. Which of these 5 choices is a vector? For mathematicians, any of these 5 choices represents a vector, but for mechanics purposes, when we say a vector, we mean a directed line segment. This is what we mean by a vector, okay. This is what we mean by a vector. This is for us a vector, that is directed line segment, okay. It is a geometrical object. It is a geometrical object and hence that is a vector, okay. In mechanics we consider this as the vector. Now let us understand what we mean by addition of 2 vectors. Say I add a dotted line segment like this and another dotted line segment like that. When I say I am going to add these 2, I bring this dotted line segment such that I move this parallelly onto this, okay. Assume these 2 are parallel, then this is the resultant vector. This is the resultant vector C. If I denote this by A, B, I write it as A plus B to be equal to C, okay. For us, if A were to be written as A1, A2, A3 and B were to be written as B1, B2, B3, then C is A1 plus B1, A2 plus B2, A3 plus B3 is, this is a special case. We will see when we can write A as A1, A2, A3, B as B1, B2, B3, but what we mean by addition is the diagonal formed by the parallelogram with A and B as the sides of the parallelogram is what we mean by addition of 2 vectors. There are cases where you can write the components of vector A and B as this and the components of vector C will become this under some special circumstances. What they are and how to, when it becomes like this, we will see subsequently, okay. Next we are interested in seeing scalar multiplication. Multiplication of a vector, that is if I have a vector A which is this dotted line segment, if I want alpha times A, what it means is, and if alpha is 2, then this vector, these are parallel lines but the length has become 2, okay. This length was L, this length has now become 2L and direction remains the same. On the other hand, if alpha were to be minus 1, the direction reverses and the length remains the same. This is remains L but direction is reversed and this would be, if this is B vector, this is the B vector here, okay. That is a B vector there. That is what scalar multiplication of a vector mean. On the other hand, a dot product means of two vectors is denoted by A dotted with B is equal to some scalar value C. This is not a vector, scalar value. Okay. What it means is, if I have a vector A, I have a vector B, that line segment, I project this vector onto this, and this length is denoted by A dotted with B. Okay. That length is denoted by A dotted by with B. In other words, in terms of length of A and B, this would be magnitude of A, magnitude of B times cosine of theta, where theta is the angle between A and B. Okay. That is what a dot product means. Here I am assuming that magnitude of A, here I assume magnitude of A to be equal to 1. So, that is why it is projection of B onto A. The length is given by magnitude of A, which is A dotted with A power half. Okay. I am sure you know all these things already. This is just a recap on certain basic operations of vector algebra and how do we represent those operations in this course. Okay. Next is cross product. We will denote this by this symbol in this course. If I have two vectors A, B, then C is defined as A cross B. Okay. C is defined as A cross B, then C would be perpendicular to this plane containing A and B. This is A, B, C is a vector which is perpendicular to this plane. Magnitude of C would be nothing but area of the parallelogram with vectors A and B as its sides. Okay. That is, I complete this parallelogram, this area denotes the magnitude of C. Okay. So, that is what a cross product does. Okay. Now, we have to introduce two symbols to be able to mathematically represent the cross product and the dot product. Okay. Delta ij is equal to 1 phi equal to j and 0 phi is not equal to j. This is called as Kronecker delta. Okay. That is, if delta 1 1 would be equal to delta 2 2 would be equal to delta 3 3 would be equal to 1, but delta 1 2 will be equal to delta 2 1 equal to delta 1 3 would be equal to delta 3 1 would be equal to delta 2 3 equal to delta 3 2, all this would be 0. Okay. So, this is called as a Kronecker delta. This is used to mathematically used for dot product. Okay. For cross product, what we do is we use the symbol epsilon ijk, which is called as the permutation symbol. Which takes values 0 if I equal to j or j equal to k or k equal to I, and 1 if I j k go in a clockwise direction, that is 1, 2 and 3 go in a clockwise direction, that is epsilon 1 2 is equal to epsilon 2 3 is equal to epsilon 3 1, all this will be equal to 1, okay, and it will be minus 1 if 1, 2 and 3 are going in a anti-clockwise direction, that is epsilon 1 3 is equal to epsilon 3 2 is equal to epsilon 2 1 would be minus 1. Note the order of index 1 2 and 2 1 have different signs here, okay. This is called as a permutation symbol, this is used for cross product. Okay. Where it is used, how it is used, we will understand shortly. Okay. Now, there is one more product that we have to see, that is called as the box product or scalar triple product. Okay. What this tells us is, gives, this is, if I have 3 vectors A dot B cross C will be denoted by A comma B comma C. This is a combination of a cross product and a dot product, and what this represents is volume of a parallelepiped with vectors A, B, C as its sites. So, basically if I have A vector, B vector and a C vector, I form a parallelepiped which is this, and the volume contained in this parallelepiped is what this scalar triple product gives us. Okay. So, we have seen 4 products now, a dot product, a cross product, a scalar triple product, scalar multiplication and vector addition. Okay. So, basically these are some vector operations that we have seen. You will see that we will use this to scalar triple product to find the volume changes when the body undergoes deformation. You will use the cross product to determine the area changes when a body undergoes a deformation and so on, when you look at the corresponding deformation patterns of the body. Okay. So, we will stop here for today's lecture. Basically in today's class we have got an introduction to linear algebra, how do you multiply 2 matrices, and then we got to know about indicial notation, what is called as a dummy index and a free index, and in the dummy index will repeat only twice on one side of the equal to sign, and a free index will appear on either side of the equal to sign. A dummy index has to be summed from 1 to 3, whereas a free index need not be summed from 1 to 3. Okay. And then we got an introduction to vector algebra. We saw what a vector is for us. A vector is a direct line segment. Okay. It is a geometrical object. Okay. And then we saw addition of what addition of 2 vectors mean, what scalar multiplication of 2 vectors of a vector means, and then we saw what a scalar multiplication or dot product of a vector means, 2 vectors means, and then we saw what the scalar triple product means, and then what a vector product of 2 vectors means. Okay. So, with this we will conclude today's lecture. Thank you.